He worked in spacecraft operation group, worked as spacecraft controller and shift manager for operations and control of geostationary satellites in around the clock shift operations. He was deputed to Fucino in Italy, Italy Interstat Ground Station to support INSAT 2D mission in the year 1997 as ISRO representative. He has worked in computer systems and simulation group and held different functional positions as head of the computer software division, manager, and so on. He worked in program and planning. He worked in planning and evaluation group. Initially as manager, program monitoring and control functioned as head of the group, and retired recently in January as the group director of SPROC systems, which is concerned with the establishment of optical telescopes, laser imaging, optical communication at Mount Abu, Rajasthan, Kerala for monitoring of Indian space assets. He's involved and participated in 50 plus satellite pre-launch activities and launch and orbit raising activities since from 1986 to 2024. He has delivered several invited talks in schools and colleges to popularize space science and computational science as a part of National Science Day celebrations, and delivered lectures for school science teachers in space science at different places over the last 15 years. He has worked as guest faculty at KM Gango 3 at Hassan to teach optical fiber communication to MSc electronics students. He is the leader of the task team to establish 3 computer labs at Government Science College, Hassan. He has published several technical papers and presented them in conferences, and he has guided many BE students for their projects. So with these few words, I request Sri H.C. Ananda to present this topic, atomic clocks, their types, principles, and applications. Over to you, Anand. Anand sir.
Thank you, Kohli sir.
Okay, sir.
You're too much. You should have cut short off your.
No, that's okay. People should know about it.
It's okay. So now, what is actually in the master control facility? We have a fleet of NAVIC satellites. That is the GPS satellites, where all in each satellite we have 2 atomic clocks. So that is being used for our Indian GPS, what we call NAVIC. So since we are operating more than 8 satellite NAVIC constellation, I got interest to see, because the atomic clocks, I just started looking at it. So with an interest looking at it, I made a module to see, and it's also, all of them is a physics application. So with that interest, I made a module. In fact, I am not an expert, but since you have seen particularly the function of atomic clocks in our on-orbit satellites, and the subsequent anomalies which we have seen in on-orbit. So with that intention, I have prepared. Now in this particular module, I have made an attempt to list out what are all the possible atomic clocks available in the world, taking into consideration the latest one which is being flown. And also I'll just touch upon, so I will also talk about certain applications where there is a project called ACES project, which is going to be done by European Space, that is yet to be launched, going to be launched in 2025. I will just touch upon that. That is called atomic. So I touch upon this in these days for the fast internet data transfer. We are going to have a Leo constellation, a small group of. There is a need of very, very high precise atomic clocks. I just touch upon one of that technology. At the end, probably I accidentally came across one particular letter from Biden administration, where they have taken a decision to define what is called the lunar time, where suppose in future, if you are going to colonize the lunar space, what kind of time scale you should have. So I just had I could get one letter, so that extracts of that letter, I will present it as a few bullets, so that you should know in future what is lunar standard time, how they are going to operate, which is going to be proposed by Biden. And the second thing is, in particular, lot of physical concepts are there. Maybe I have just mentioned and the material is little bit exhaustive. Probably, if possible, some places I may just run through that so that I should be able to cover in an hour. And let us see how it goes. Thank you for giving an opportunity. Let's proceed. Okay. Yeah. See, atomic clock definition. See, atomic clock is actually a device or a time standard which uses hyperfine transition frequency in the microwave region or an electron transition frequency in the optical region, where as a frequency standard to keep a timekeeping element. In also, we can also define as atomic clock is a precise clock that depends on its operation, an electrical oscillator regulated by a natural frequencies of an atomic system. Now, because we have the quantum computing is coming into a lot of research is going on. Scientists are imagining to measure quantum atomic clock experiencing two different times when they are placed in superposition. Still, it is in the research is going on. So, clocks are actually the most accurate in the frequency standard used for international time distribution devices to control the wave frequency of television broadcast, GPS systems, and the IRNSS is our NAVIC constellation. In general, we have the three types of atomic clocks, which include cesium, rubidium, and hydrogen maser clocks. Now, if you look at the principles, the atomic clocks actually they use the electronic transition in atoms, where the electrons change the state from one state to another. They take advantage of the fact that all the atoms in a particular element will have the similar electronic configuration like cesium and rubidium. Now, if you look at the principle, just to briefly talk about, the electrons are moving around in nucleus. They occupy a small number of defined states which have a defined energy. In an atomic clock, a certain frequency photon is incident are shown on that. If the energy of the incident photon is equal to the energy level difference, then the atom absorbs the photon and changes over to the excited state. And this process is repeated again and again to see that the efficiency of the executive is constantly monitored and the frequency of light is also corrected to yield the highest efficiency. Now, in other words, the atoms that constantly watch over the frequency of the light source, which in turn can be counted and measured and used as an event. So, this is the principle being used. The energy difference between the contact state is a constant ratio of atoms. And however, the external electromagnetic fields can enhance the energy states and the transition frequency. So, to the extent possible, the atomics are shielded to the greatest extent for these perturbations. In general, the principal operation of an atomic clock is based on measuring the electromagnetic signal, a photon emitted by the electrons on the transition. Since 2004, what we say that the atomic clocks, they try to first cool the atoms to a near absolute difference and slowing down using the lasers and then program in atomic fountains, which is nothing but a cavity which will microwave field cavity. And basically the NIST one, that is the NIST F1 clock, is one of the primary and the frequency standard used by the United States. They have NIST F1 and F2. In NIST F1, they found out certain deficiencies which they corrected in NIST F2. Now, if you look at the history, the idea of using atomic transitions for measuring the time was suggested by Lord Kelvin in 1879 itself. And magnetic resonance, which was developed in 1930, became the first practical method for measuring atomic time using transitions. The first atomic clock was built in 1949 by US Bureau of Standards. The atom was an harmonic absorption line in the frequency near 23,8000. It was less accurate compared to current day clocks. The first accurate atomic clock was built in 1955 by UK National Physical Laboratories using cesium as a standard, cesium 133. Now, the calibration of cesium standard clock was carried out using what is called the astronomical scale ephemeris time. There are different time scales. So, the cesium clock is actually the calibration is done this. And because of this, the definition of second was done based on the cesium time in the year 1967. Now, since the beginning, the atomic clocks were based on the hyperfine transition of the three elements, that is hydrogen, that is prosium, cesium-133, and rubidium-85, all the stable isotopes. The first atomic clock was what is called the atomic chron, was by a national company. Initially, atomic clocks were too bulky and expensive. Later, rack-mountable atomic clocks by HP 5060 using cesium frequency stand was released in 1964. And the chip level atomic clocks was demonstrated by 2004 by National Standard Agency of US, which required a power of around 125 milliwatt, make it portable for a battery-driven application, and became commercially available in 2011. Later, ion trap experimental atomic clocks were more precise than cesium clock. By the year 2015, in order to for the deep space navigation without depending on the GPS signal coming from that, and for the autonomic navigation for interplanetary mission, the NASA developed what is a type of atomic, a deep space atomic clock, which is based on ultra mercury atomic clock in outer space. And this actually deep space atomic clock is more stable than compared to conventional navigation clocks. That is a typical pictorial representation of some of the atomic clocks, cesium and other things. And this is the deep space atomic clocks. Now, when we try to look at the accuracy, the atomic accuracy depends on the two factors. One is the temperature of the sample atoms. Colder, as and more the atomic colder atoms, they move slowly, leading to longer. Means in order to get the transition frequency, you have to probe more number of times. And frequency and the line width of the electronic or hyperfine transition. If you have a higher frequency and a narrow line width, they use to increase the precision. And national state, see what happens is, in order to get a precise time, the different national standard agencies across the different countries, they maintain a network of atomic clocks, which are intercompared, and they kept synchronized to an accuracy of 1 second per day. These clocks are collectively defined a continuous and a stable international atomic time called TA. For civilian use and other things, there is another time which is called the coordinated universal time called UTC is disseminated, which is derived from QA, which also accounts for a leap second added to account the rotation of the Earth with respect to solar time. Now, just to touch upon the hyperfine transition, just for the benefit of others. Now, suppose when a transition takes place at the resonant frequency, splitting up of a spectral line or a molecule and atom into two or more closely spaced component as a result of the interaction of the electrons with the magnetic moment is called a hyperfine structure. And hyperfine structure is basically defined by small shift in splitting in energy levels of the molecule ion because of the interaction between the state of the nucleus and the electron clouds. In other words, with respect to cesium standard, the hyperfine transition refers to the radiant of photon produced by due to the transition between the two hyperfine stated of cesium-133. That is a typical pictorial representation. Now, cesium standard. So in the 1967, the definition of second was redefined by International System of Unit. They defined means this many number of cycles, that is 9, 1, 1, 9, 2, 6, 31, 7 cycle of radiation corresponding to the transition of two energy levels from ground state of cesium at absolute zero. That is defined as 1 second. And cesium standard is the primary frequency standard in which photon absorption between the two hyperfine ground state of cesium-133 are used to control the output frequency. This definition makes the cesium oscillator as the primary standard for time and frequency measurement, which is called as the cesium standard. In this design, so if you look at the basic of this, in this design, actually a reference atomic clock consists of an oscillator and a microwave frequency. The frequency determining component of the oscillator contains an element which is controlled by a feedback signal. The feedback signal keeps the oscillator tuned to resonance with the hyperfine transition of cesium or rubidium. Now, if you look at the mechanisms, the radio frequency atomic clocks, which contains a tunable microwave quantity containing a gas. In a hydrometer clock, the gas emits microwaves on hyperfine transition. The field in the cavity oscillates and the cavity is tuned to the maximum microwave amplitude. The atoms in the graphs are prepared before the probe atoms are prepared for one particular fine state. In rubidium or cesium clock, the gas absorbs the microwaves and the cavity contains an amplifier which makes it oscillate. The atoms in the gaps are prepared again to a particular hyperfine state before filling them into cavity. The number of atoms which change the hyperfine state is detected and the cavity is tuned to the maximum and the changes are detected. Now, if you try to compare the atomic clocks, the rubidium clocks are very popular and it is of low cost and its size is very small of the order of 17 centi-cube, and it has got a short-term stability. Basically, they are used for commercial and portable and aerospace applications. Hydrogen maser clocks are very superior short-term stability compared to other standard, but they don't have a long-term stability. What is done is sometimes one standard is used to fix another. For some of the applications, what they use as rubidium standard is periodically collected using a GPS receiver, which is also called as a GPS disciplined oscillator. This also achieves a short-term accuracy along with a long-term equivalent to US national standards. So CCM atomic clocks have a very high frequency accuracy and a good frequency stability without long-term frequency dips. So basically, CCM clock is the largest and most popular used atomic clock used in the mass production across the world. Now, if you take at the lifetime of a standard, the modern rubidium class lasts for around 1 decade, and it costs as low as $50 to $100 to few thousands of dollars. CCM reference tubes, they are suitable for the national standard. They last for 7 to 10 years, which costs around 35,000 onward, 35,000 US dollar onwards. The long-term hydrogen mesers are standard. Their efficiency will decrease because of changing cavity properties over time. The modern clocks, they use what are called the magneto-optical traps to cool the atoms, and they show an improved precision. When you look at the power consumption of atomic clock, they vary with their size. The atomic clocks of if you have an atomic clock of a chip size, it requires a power of less than 30 milliwatt. Whatever the national the CCM fountain class used by US national standard, that is NIST 1 and NIST 2, they use higher power. Now, if you want to look at the evaluated accuracy, there are two largest sources of measurement uncertainty which comes in atomic clocks. One is what is called the distributed cavity phase, and the other one is the microwave lensing frequency. The evaluated accuracy and the priming standard to the 10 to the power of minus 15 as in 2015. The NIST F2 cesium fountain clock operated by the NIST of US for civilian and frequency standards in 2004 has shown a evaluated accuracy of 1.1 to 1.5 10 to the power of minus 16. The planned accuracy is around 1 into 10 to the power of 50. With this planned accuracy of 1 into 10 to the power of minus 16, the NIST F2 fountain clock, cesium fountain clock, is not supposed to lose a second in 300 million years. Now, the advances in NIST F2, they made changes. There are some problems were observed in NIST 1 operation. To correct that, with respect to NIST 1 is that the vertical flight tube is chilled inside a container of liquid nitrogen to minus 193 degrees centigrade. This cooling reduced the background radiation and a small measurement errors which was encountered in NIST F1. So these corrections they made in NIST F1 to get a more precise and stable atomic clock in NIST F2. Now, quantum clock actually is a typical atomic clock which a laser cooled single ions confined to a electromagnetic ion trap. In 2008, the NIST physicist described what is another called as the quantum logic clock based on the quantum logic, where the individual aluminum, beryllium and aluminium, the logic atom, clock called ion vibration at an optical frequency, which is almost used in NIST. In 2010, NIST physicists described what is called the enhanced quantum logic tag based on the individual ions of magnesium and aluminium. They could achieve a frequency accuracy of around 8.6 to 10 to the power of minus 18. In July 2019, the NIST scientists demonstrated the aluminum quantum logic clock, which has an uncertainty of 9.4 into 10 to the power of minus 19. So this is the kind of the accuracy level the present day atomic clocks they expect. The accuracy of quantum clocks has been superseded with the invention of the experimental optical lattice clock based on strontium. This accuracy has been superseded. Now, just to touch upon before going to the optical clocks, I just touch upon the physical principle of physics people are aware of. An optical changes one energy states to another and absorb in the either in the visible or the IR region. An optical transition filter is designed to model the optical absorption or the stimulated emission of radiation in semiconductors. Simulated emission or absorption occurs when a transition takes place between the quantum state in the presence of an oscillating field by propagation of the electromagnetic wave. In the case of semiconductors, simulated absorption occurs when an electron in the valence band absorbs a photon and transits into the conduction band. And similarly, simulated emission and spontaneous emission people are aware of. An optical clock. See, in the year 2012, David J. Winland is a pioneer in exploiting single ion held in a trap to develop clocks of the highest stability. Now there are latest technologies which have come, what is called the femtosecond frequency combs, the optical lattices, the quantum information based on the entanglement. The research is going on, a prototype of the next generation atomic clocks. All these clocks are based on optical transitions. But the difficulty which was faced in developing optical clock was the difficulty in measuring the directly measuring the optical frequencies. The problem was solved with the development of what is called the cell reference mode laser, which is also known as femtosecond frequency combs. In this, an absorption spectroscopy is used to stabilize the oscillating the laser. Now, when the optical frequency is divided into countable RF signals using a femtosecond comb, the bandwidth of the phase noise is also divided by the equivalent factor. Even though the bandwidth of the laser phase noise is greater than the microwaves, after division it becomes less. So, in that way, it is more stable. Now, the systems considered for the use for optical frequency standards, these are the one is what is called the single ion isolated in an ion trap, the neutral atoms trapped in an optical lattice, atoms packed in three-dimensional quantum gas lattice. These technologies allow atoms highly isolated from external perturbation, including stable reference. The atomic system considers the different kind of ion, magnesium, strontium, ytterbium. So, a particular transition of ytterbium atoms at a frequency of 500 nanometer is more accurate compared to the optical frequency standards. The optical class, say actually what has happened is, no, I have not just touched upon, there is another concept of optical lattice, like conventional lattice, what we have in a crystals. In 2013, optical lattice clocks were shown have a better efficiency than cesium fountain clocks. So they two optical lattice clocks containing around 10,000 atoms strontium, they stayed synchronous with each other at a precision of around 1.5 into 10 to the power minus 18, which is accurate enough experiment could measure. In the year 2013, yttrium 171 atoms, a precision of the order of 1.6 to 10 to the power of minus 16 was achieved. Now, and yttrium atoms, which is put to a 10 microkelvin and trapped in an optical lattice. A laser at 578 nanometer used to excite the atoms between the two energy levels. Now, in the 2017, GLI reported an experimental what is called 3D quantum gas optical clock, in which strontium 87 was packed in a very narrow tube of which is densely populated compared to 1D clock. It yielded a synchronization of 5 to 10 to the power of minus 19 in 1 hour, averaging out. The important component of the 3D clock was unusual state of which is that which contained the what is called the degenerate Fermi gas. The important potential was scale up the atom numbers and gain stability. So this is a pictorial representation of an optical class. We have active frequency tandem, control electronics, a reference of a cesium clock, and an optical output. Next is the nuclear clocks. See, basically, as of now, the nuclear clock is only research is going on, and still the one possibility of improving the performance of atomic clock, the use of nuclear transition of different nuclear isomers rather than the electronicization, in which the atomic clocks measure. Most of actually, when most of the nuclear transition, they operate at high frequency to be measured, but in 2003 it was shown that a low excitation energy of thorium-229 is within the reach of current excitation measurements. In 2012, it was also shown that a nuclear clock, a single thorium-229 provided a fractional frequency inaccuracy of 1.5 to 10 to the power of 19, which is better than this. So when you have as of now, nuclear clocks have not been developed. It's still research is going on. There are some design difficulties. The nuclear energy transition offers the following advantages. The higher frequency transition offers a greater stability for statistical reason because the fluctuations will be averaged over a number of cycles per second. See, this is typically some of the actuaries achieved just to have a comparison. A CCM clock which is based on, which relies on hyperfine transition, the accuracy is around few parts of 10 to the power of minus 16. Using optical lattice clock, they use laser cooled atoms in an optical lattice. They have achieved the accuracy of the 10 to the power of minus 18. And similarly, strontium and yttrium clocks, which uses optical transition principle, also achieved an accuracy of 10 to the power of minus 18. However, the deep space atomic clock, which already in the coming slides I will just explain, where the achieved accuracy is of the order of few nanoseconds over days or weeks. So when you see, what happens is, achieving high level of accuracy requires not only advancement in atomic physics and latest technology, it is also essential to control the environment factors that can introduce noise and perturbations. Now, when you look at the nuclear class, the advantages are the immunity to environment effect because of its small size and shielding. The surrounding atomic nuclei is less sensitive to the ambient electromagnetic fields than electrons. Because of the immunity to the environmental effect, it's not necessary to have clock atoms well separated in a dilute gas. Atom can be placed in a solid, which allow large number of atoms to be integrated or crowded so that you get more stability and efficiency. Now, suppose if nuclear clock becomes a reality, the nuclear clocks can be used to test the fundamental physics. The nuclear resonance frequency is determined by a strong and a electrons possible to build a precise nuclear clocks can be used to do high sensitive tests like such equivalence principle. Okay, you are able to hear? Hello?
Yes, we can hear. Please go ahead. Go a little slower. I think you are going too fast. Please go slowly so that people can follow. Yeah, we can hear. No problem.
Okay. Nuclear clocks can be used to do highly sensitive tests like research in violations, Einstein's equivalence principle, and new particle interaction beyond the standard model. It is proposed to use nuclear clocks to search variation in the electron and strong coupling constant and dark matter research. And two types of nuclear clocks, namely a laser-cooled trapped thorium-29 ions experiment with complete control of nuclear interaction reaction, and thorium-doped solids enabling experiment to high particle number in a different electronic environment. These two are being proposed. Now I just touch upon one project which is taken by ESA, which is called a FET project, which is also called as UCOC. It is aimed at creating high accurate nuclear clocks. See, the problem is with the atomic clocks which are there, currently interference from the environment, particularly from the atmosphere, is the main limiting factor for the accuracy of atomic clocks. In nuclear clocks, this interference is very, very low, which is almost six times pressure, is much better than atomic clocks, which has accuracy of 10 to the power of 9. In case the nuclear clocks becomes a reality, it will have an entirely striking effects on many areas of application like navigation, telecommunication, GPS signaling, and high-speed mobile networks. Most accurate atomic clocks drift by an amount of 4 seconds since Big Bang. Before making nuclear clocks reality, there are two things has to be made confirmed or essential: the precise frequency of light needed to excite a thorium nuclei, and also we should be able to identify the transition. And nuclear clock will shed light to the string theory. Now, the frequency of jumps in a nuclear clock will depend on the strong nuclear force. Jump by electrons in atomic clock depends on a different fundamental force. So this is actually a teaser that. Now, when we try to compare the atomic clocks and the nuclear clocks, in atomic clocks actually they use elements of yttrium and strontium which are irradiated by lasers. This process actually excites electrons in atomic cells and make them to oscillate between different energy levels. The resulting oscillation created when the electrons shift between energy levels, which is triggered by a wavelength of electromagnetic radiation. So atomic clocks actually they require less energy for transition compared to nuclear clocks. Nuclear clocks actually uses the same principle, except that it depends the oscillation of nuclei itself instead of electrons. Atomic nuclei require actually very high energy of the order of kilo to megawatt to be excited enough to oscillate. It needs in the scale of X-rays. However, among hundreds of atomic nuclei, thorium-2229 is appear to be a suitable candidate. An exception, it requires a much less energy in the form of few electron volts. This is solar that needs only ultraviolet irradiation to oscillate. Now, if you look at what kind of applications they have, atomic clocks are actually used for for precise global and regional navigation systems. They are also used the applications on the internet, and it also used for sites of time signal and radio transmitters. It is used for some long wave and medium wave broadcasting station to deal precisely carrier frequency. In scientific distribution for long, what is called the very long base interferometry for radio astronomy. Now, just we will touch upon the atomic clocks ensemble in space, which is the project is taken by the UNCERT Space Agency, where the launch is expected to go in 2025. So, atomic clock ensemble in space is a project led by ESA, which will place two ultra-stable atomic clocks in the International Space Station. The operation of these atomic clocks in the microgravity environment provides a stable and accurate time based in the different areas which include general relativity, string theory, and frequency metrology, and also VLBI. Now, when the satellite, this one is payload, the satellite is launched, which restricts that the payload will contain two clocks actually. One clock is a CCM laser cooled atomic clock, which is called a Ferro, developed by the French Space Agency for a long-term stability. An active hydrogen measure, HHM, is developed by Spectra of Switzerland for a short-term stability. Now, they want to compare these two atomic clocks, which one looks for a long-term stability, other looks for a short-term stability. The onboard frequency comparison between ferro and the short-term stability is a key for the evaluation of accuracy, whether short-term or medium stability of the ferro clock. It allows to identify an optimal operating condition for both ferro and select, depending on the kind of application, whether you have to make a compromise between frequency or stability. When atomic clocks are operated in a space lab laboratory, the large variations in gravitation potential or velocities variations and access to ground clock becomes a key element to tiny, because any tiny deformation in space-time might bring the signature to new physics. See, the atomic clock ensemble in space has the three mission objectives: measurement of gravitational redshift and search for sign drift in fundamental constant, search for violation in special relativity. So the working principle, actually what they are trying to do in ACES is designated to test the Einstein's equivalent principle using high performance atomic clocks on space and ground. It is going to be installed on the ISS. The ACES payload actually, it generates a clock signal with a fractional frequency instability and accuracy of the order of 1 to 10 to the power of minus 16. Now the ACS payload actually distributes its time scale of atomic clocks by using two independent channels of time frequency and using two different transfer links. And there are two links. One link is operating in the microwave region, other one is optical frequency. Will allow comparing the ACS clocks on the ground, which are network. On the ground, actually, the microwave clocks on ground terminal and also satellite ranging station will provide a physical interface between the ACS clock ensemble and the atomic clocks on ground. So comparison of the space to ground and ground to ground of comparison will test the Einstein general theory of relativity. It is also expected to the free fall condition, which is very, very crucial for ferro clock to reach the performance best known atomic clocks in the world. The ACS payload has a volume of around very small, and at a kg, the total mass of the payload is around 230 kgs. It has a power consumption of 450 watt. And okay, this is another additional detail clock stability. Now, typically, Einstein general theory is familiar. See, identical clocks placed in different gravitation potential, they experience a frequency shift depending on the notation potential of the clock position. When you compare the onboard ACCS clock and the ground-based clocks, the frequency variation due to gravitation-led shift and testing the Einstein prediction between a fraction of 2 ppm is an unset level. Now, as per the Einstein theory of relativity, the gravitational shift is a phenomenon where the photon travels to a gravitational level, it will lose energy. The loss of energy will decrease if the photon frequency and equivalent increase in wavelength. So as a result, if the two clocks operating at different gravitation potentials, a clock operating in a higher gravitation potential is ticked faster than a clock operating in lower gravitation potential will have a higher measured frequency. So basically, the gravitational frequency is a consequence of Einstein's principle of gravity and acceleration. They are equivalent. So this is a typical pictorial representation. See, atomic clocks, this mission will become a test bed for space qualification. Also, actually, the active hydrogen measure is not space qualified. So this mission, they want to qualify the hydrogen active measure on an ISS. After optimization intended performance, the frequency instability should be in the range of 2 to 10 to the power of -16. And the clock ensemble is expected to travel to ISS by a SpaceX Falcon rocket, and it will be mounted at the Columbus laboratory. It is supposed to operate for around 18 months. So this is the typical the rocket which is going to take the ACS payload, and this is actually the once it is installed, how they communicate the pictorial presentation of ACS communication with the ground station to compare the two onboard clocks with the ground station. Now let's just touch upon the deep space atomic clocks. A deep space atomic clock is actually a critical step for enabling spacecraft safely, independently navigate autonomously, rather than relying on a time-consuming process of receiving instruction from the ground-based laboratory. This was developed by NASA's JPL for the first time to keep stable enough to maintain the spacecraft trajectory in deep space and small enough to be housed on a hand. So deep space atomic clock is actually a miniaturized, ultra-precise mercury ion trapped atomic clocks for precise radio navigation in space. So it has been refined that it drifts only by 1 nanosecond in 10 days. So actually DSAG will not occur not more than 1 nanosecond in error or 1 millisecond error in 10 years of operation, and it is a stable. See, for example, for a deep space network, the accuracy of nanosecond is more than enough to navigate autonomously. Whereas for time synchronization error, you need an accuracy of 10 to the power of -15. Actually, the project is managed by NASA's JPL, and it is developed as a part of Air Force program STS-2. The technology actually enables for autonomous radio navigation of the spacecraft, even orbit insertion. Suppose if you have got an interplanetary mission where you want to bring a spacecraft to orbit around a planet and precise landing, and it is expected to improve precision of deep space navigation, enable using tracking network, and a significant reduction of ground support operations, so that economy is also taken care. It is a typical the deep space atomic clocks. Now, deep space atomic clocks actually uses a principle, technology uses a property of mercury hyperfine transition frequency of 40.5 gigahertz to effectively steer the frequency output of a quad oscillator to a near constant value. So DSAG actually does this by trapping the mercury ions with electric fields in a trap and protecting them by applying a magnetic fields and shielding. So DSAG development actually includes a test flight and put the satellite in a lower pitches and demonstrate a precision orbit determination. The flight actually is being hosted on 4 other payloads on orbital stack. It was launched for a low orbit in June 2019 using a SpaceX Falcon and approved for further use. Now, there are actually for nano and micro satellites being launched. Actually, this is a big constellation. There is a heavy demand for increase the data rates for the internet, so that a constellations of very small satellite of around 150 to 200 kgs, hundreds of them, putting in the low Earth orbit. For nano and micro satellite in low Earth orbit are the unmanned serial vehicle base in the stratosphere are considered to be used for increasing coverage and provide on-demand data of internet for mobile communication, even for the 5G technology. To achieve this, a low cost and a miniaturized time standard atomic clock is required. Very, very, very small and low power. See, one of the key technologies for high-speed and long-distance communication of LEO translation is a very accurate time standard atomic clock assisted satellite. But what happens is the GPS can be a primary sufferers, but they suffer from a large path loss and also degradation in accuracy in the receiver part. So GPS cannot become an always available in space. When the conventional atomic clocks have deployment difficulties in a large array due to large power consumption and volume, you have to look at atomic clocks of a very small with a very small power. So due to a special condition of atomic cell required for a reference frequency locking and even probing in a compact atomic clock, the size should be of the order of 120, 150 centimeter by 770 km. It has to consume a very small power of the order of 1.2 to 10 watt of power. So now there are actually the technological development which has happened in the photonics and the MEM processes. It is possible to realize a low power, a small volume quantum package atomic clock based on what is called the new technology called the CCM coherent population trapping method. With the reference frequency locking and probing techniques realized by using the CMOS ICs, it is possible to manufacture a small factor atomic clock. Whatever I told, ultra power low atomic clocks, which is well suited for low Earth orbit satellite constellation with cesium gas cell with a vertical cavity surface emitting laser. The prototype has been developed. So typically, when I want to measure the efficiency of this, one parameter which is used as the Allen deviation, which gives the deviation, how output frequency is stable over a time, which should be of the order 2.2 to 10 to the power of minus 12. And some of the physical experiments which are planned with atomic clock using optical lattice clock, a gravity physicists of the University of Princeton are developing a gravity experiment using optical lattice clock. Optical lattice clocks, they use atoms lined by lasers in a nodal grid as a frequency. They build a clock containing two. They were planning to have build two optical lattices and allow one lattice to fall and accelerating the other in the horizontal. By doing this, they want to create Einstein's equilibrium principle, which is say that gravity is indistinguishable from a non-gravitational accretion. The most precise clock in the world has to tick 30th before losing 1 second. So within as of now, an atomic clock will expect to lose a second in 33 billion years. So another avenue of features of launching atomic clock in space, that is atomic clock in ensemble base, which already I have told you, to orient, that is deep space atomic clocks, where the spacecraft will navigate autonomously without getting the signals, which is the DSAC for interplanetary mission. And also very baseline along interferometry to improve the measurement. The researchers have started developing the research facilities with a single sign standard is called using an optical fiber network. Synchronization actually results in improvement in astronomical imaging, what called the VLBI. So VLBI actually involves a multiple observation, you are working together to image, which is otherwise not possible to resolve using a single telescope. Astronomers used to capture the first image of a black hole using VLBI. Better synchronization you will for high resolution imaging. So this is another application of this. Now this I just touched upon. Now what I told about is in April 2nd there was some kind of a letter taken by the Biden administration. They approach to establish time standard which contains the development implementation for the lunar colonization. So they look at what is called the traceability, accuracy, and this. So NASA, in coordination with the Department of Commerce, they are trying to implement this standard actually. So NASA actually, they are interested in defining what is called the coordinated lunar time, LTC. So what is the challenge is actually US government is anticipating many state actors, which include government and private agencies, where they're trying to send spacecraft to operate in what is called the cislunar space, which includes lunar surface, means exploring the lunar surface in lunar orbit, the Earth-Moon Lagrange points. So what is required is a unified standard which should be functional to all these efforts. The National Cellular Science Institute is going to establish what is called the cellular ecosystem with a scalable and interoperable navigation timing infrastructure. And they are also and this time standardization is essential for the foundation for the interoperability of different user agencies and the international promote for the safe and promote a sustainable operation, and even including the space situation awareness, which is that the debris monitoring for flight operation. Now, the technical background, actually, the universal, whatever UTC which is used, is going to be used as a primary time standard for Earth-based systems today. And actually, what happens is relativity poses actually a challenge to extending operations into lunar space and beyond. Now, due to general and special relativity, the length of a second defined on Earth will appear to be distorted on the lunar surface under different gravitational conditions. In fact, if you look at an observer moving on high relative velocity to an observer on the moon, an Earth-based clock will appear to lose an average of 58 microsecond per day with additional periodic variation. This holds important implications developing capability for operating on the surface of the moon. Secondly, the navigation accuracy in a system can achieve signals on multiple space systems. Suppose if a person is navigating on Earth and where he is trying to synchronize his signals from a GPS assisted satellite and or GPS synchronized with respect to assets with each other, but at the surface of moon, synchronizing each asset on the lunar surface based on a time standard on Earth is very, very difficult due to relativistic effect and events that appear simultaneously are not. So safety of navigation in cellular space also refines, and you have to define a consistent time which can be synchronized on the lunar surface. So there are certain other limitations. So with this now, and also beyond this, using of the direct use of the whatever units time used on the Earth, it is not possible to use on the moon surface because it will have a cascading effects on the application that requires precise metrology, and also whatever the units which are being used, like SI units, which are used for the core definition, calls for non-SI unit to account the relative weightage, which disturb. So these type will have an undecided impact, such as reducing the accuracy or navigation. So that's why the NASA is going to define what is called a coordinated lunar time, which is called LTC, which they are going to propose, which acts as an established standard to enable the cislunar operations, means all the users, all the flights, or the probing, and they has to be synchronized with UTC. The concept of lunar time is similar to an idea of terrestrial time on Earth. Just as on the Earth, the terrestrial time is actually synchronized using the ensemble of atomic clock, which are synchronized, comparing that. Finally, what I already told you, that universal UTC is disseminated for a civilian use. In another, the leap second is added. Similarly, in order to on the in an ensemble of clocks on the moon, we said this operational standard LTC may directly employ to distribute usage offset required for both local time and UTC in the specific tolerances. So using what is called the lunar tracking time uses a cellular space which can be used as a time reference standard for a near gravitation. And suppose it, because the gravity environment is different both on Earth and the lunar surface, so that synchronizing with the lunar time, this approach supports both compatible standards for the users and the space to Earth and assets which can synchronize accurately on the timing systems. So NASA is actually, they are trying to standardize this, or NASA in coordination with this, they are trying to what we define and make what is called a coordinated lunar time, support gradual establishment of lunar infrastructure or the colonization of moon. So the conclusion is the exploration of cislunar space, or the lunar, that is the exploring the moon or going to the moon or Earth to moon boundaries, is a new opens a human activity and offers opportunity for advanced scientific thinking, exploration, economic growth. So with this, I just end my presentation.
Thank you very much, Ananda. Now there's time for some questions or comments. If you'd like to make them, please raise your hand and then you can speak. Anybody would like to ask any questions or make any comments, you can raise your hand, then you can ask. In the meantime, since nobody is coming forward, I have several questions. What about India? Does India has atomic clocks, especially like NPL and ISRO, they must be having. And
No, already I told you, sir. That is, we have a NAVIC constellation of 8 satellites,
Yeah.
and out of that, for all our GPS application, minimum 4 should be visible at a time. So actually, what is being done is we have two centers. That is, one center is there in Hassan. Actually, master control facility. We control the satellite, but the commands for the GPS grid correction and the navigation things, the commands are generated from Bangalore, that is Pune. We have the bylaw. So they generate the commands every 5 minutes. The commands are generated and comes to Hassan and gets uplinked to the satellite. Okay. So the grid correction and the atmospheric correction commands automatically comes and gets uplinked to the satellite through our computers. Okay, that is one thing. Second thing is to find out the accuracy and all this. They do the ranging is done from a set of ground stations called the TRDM stations. They collect the ranging and finally they do the orbit determination. The OD data is percolated to us also. But at the end, I told you that SPROC project, I already told which way I was working, satellite photometry, laser ranging. The laser ranging is the part where we wanted to calibrate the atomic clocks on the navigation satellite by setting a laser signal. Okay. So that project is yet to be commissioned. So once that is done, the laser calibration for precise synchronization being used. At present, the NAVIC constellation is being used, which is equivalent to the GPS of US. NAVIC.
Okay, thank you. Any other questions? Okay.
Can you hear me, sir? It was
please go ahead.
very nice talk. And somewhere in the middle, the speaker was mentioning the relativity effects.
Yeah.
Can you elaborate on the relativity effects and the stability of these clocks? I mean,
that is what I told, sir. That is actually it has been told by Einstein that suppose if the two clocks are placed in two gravitational potential, the clock which is operating in a gravitational potential will tick faster. So there is a frequency shift. So that they want to prove by an experiment, which is yet to be done. So whatever theory Einstein has told, they want to prove through an experiment using these experiments. Okay. So that's still whatever that ACES which is going to launch in 2025. So there are a lot of physics experiments being planned. So whatever I have mentioned, still this launch has not taken place.
Okay.
For the people.
Thank you, sir. Thank you very much.
I have. Okay.
Yeah.
I have another very simple-minded question. You said cesium-133, one of the earliest atomic species to be used for atomic clocks, isn't it? Now, what is the advantage? Why cesium-133? What is the reason? Could you explain it in simple terms? Why that particular atom?
The cesium and rubidium is actually that one initially they found out. Initially when compared to whatever the hyperfine transition, these two, cesium and rubidium, were the two elements which they found out they could measure the hypertransition frequency, and in 1960 that they make it as a standard to define the whatever the so-called the International Time Agency. They take it as this is the most best precise way of measuring, precisely they can measure the transitions. So that they have chosen by the International Atomic in 1968.
Okay. Any other questions?
Now, only thing is too much physical concepts. That's why I said no.
Yeah.
For example, one just I wanted to. Anyway, yesterday I was looking at it. Any other latest trends in this? Now there is another concept. What is called super radiant atoms. Super radiant atoms. They are trying to use the concept to make the accuracy more than 10 to the power of -19. So basically, what happens is now these electronic transitions. There you try to only one electron. You go to excited and it comes down. In a super radiant this one, you will have multiple excited atoms or electrons. They do the transition once together, where all of multiple atoms will be there in the accurate signal for transition frequency. That research is being done. Means super radiant cooler atoms, where you will have multiple atoms transiting simultaneously, giving you very sharp and a peak signal, which will be more precise and stable. So the technology is being proven actually by one of the universities, but still it is there in the laboratories. So that if it becomes a reality, probably the accuracy they expect is more than 10 to the power of minus 9.
Okay. Any other questions?
And secondly, I want to.
Okay,
So
please.
this is
Ah.
Professor Vijay Kumar Dodmani sir from Bangalore University. One more related to the astrophysics thing, sir. Like the pulsars are considered as the most precise celestial clocks. How close the accuracy of these the man clocks, the man-made clocks, are closer to these pulsar timing systems?
Frankly speaking, I don't know what is the frequency with which these pulsars they are radiating. If I know the number, it should be around 10 to the power of, that's why I told the best atomic clocks as of now, it is around 10 to the power of minus 19. That is the inaccuracy with which. Now, the frequency, if you try to, what is the frequency with which the pulsars are radiating, probably we will be able to compare. At present, I don't know what is the number of.
I meant in radio, sir.
Radio frequency.
That's what I'm telling. That is whether, what is that order, if you try to compare, it should be that number, I don't know.
Okay.
Okay, sir. Thank you.
So if there are no further questions, I would like to thank the speaker and the participants for attending this Zoom meeting and making it a very successful event. I would also like to thank Jnanadhara, in particular Dr. M.K. Raghavendra, for providing us technical support very promptly so that we can conduct these meetings. So next week also we'll be having at the same time another talk. Probably actually 3 people are ready to speak next Sunday, but we'll choose one of them. And please join us. You'll be given the meeting this thing code, meeting code or meeting link. So please join us and participate in these activities. Thank you very much.
It was too exhaustive.
Yeah, too much material for people to understand.
I told no, this is because if you what happens is there is a lot of technological advances which is going on. I just made at least an on-site so that people are aware of these are the things. At least one can Google or just see that. And I just wanted to tell you because yesterday I was not aware. And actually I was what is called optical lattice. I just mentioned. So actually optical lattice is created by intercepting the laser beams in a way they forms a particular periodic potential of neutral atoms. So you will have a dips actually. See, the atoms will get trapped in the wherever the low potential is there. So it is since it is like a sort of an egg cartoon where the atoms will get trapped at the location of lower potential it is analogous to a crystal lattice. That is called an optical lattice.
It's too much high.
I was not knowing the definition. I just found out because like this, so many small, too many physical concepts are there.
Very high technology stuff is there.
No, that's why I said. That's why probably I have touched upon all the best atomic clocks available in the world, and even I have just touched upon what NASA has done using this and this. Whatever this particular our OneWeb, where they are recently launched some 500 satellites for internet broadband. What kind of clock they are going to use? UPL clocks. Okay. And similarly, I just touched upon the super radiant, which I could not get much literature on that. But anyway, I will try my level best to give the latest technology what is available as of before.
People will now start, once they have heard of these words, they will go ahead and look up the books and try to understand more details. Okay, thank you.
Last 2 slides are from the April 2nd letter which came from the JP, where they want to define what is called the lunar time, like UTC.
Okay, please end the meeting. Since you are the host, press the button, end the meeting, and the meeting will be closed.
Okay,
Anand, sir.
Oh, okay, sir.
Yeah, please press the button, end the meeting, so the meeting will be ended. Because you are the host, you can only do it.
Okay, sir.
End the meeting. That button is a red button. A red button to the right side, I think your right side, on the right corner of the screen.
Presentation on this there, one second.
No, right corner, it will be the end the meeting. Since you are the host, only you can do it. We can only leave the meeting, but you can end the meeting by pressing that button, red button.
And I'm just seeing, sir. It's
Yeah,
not
yeah.
visible.
It says end the meeting. End it for all. No, at the bottom, bottom line. Then we end the meeting. Right side. Somewhere.
I'm not able to see that.
Okay, then we leave the meeting. Each one of us, we can leave the meeting. No, the bottom side, bottom left, right side.
No. After sharing, it came actually. After stop sharing, because that it was not visible.
Okay.
Unless I stop the sharing. Okay,
Okay.
sir. Anyway, I will be out of country for another.
That is why we
join you after 3 months.
That is why we asked